ever wonder what it'd be like to, like, if you could just peek behind the curtain of reality, to see the universe, like, at its most fundamental level?
Hmm.
That's what we're doing in today's deep dive.
Yeah.
We're going straight into that subatomic realm, checking out how quantum computers, get this, might soon unlock secrets of particle physics, and they've been totally out of reach until now. Wild, right?
Yeah, and it all starts with a bang.
Okay.
Well, more accurately, a lot of bangs.
Okay.
We're talking particle collisions,
Uh,
so energetic that they create a cascade of subatomic particles. It's called a Parton shower.
a Parton shower.
Imagine like a subatomic fireworks show. That's
Right.
the kind of chaos we're dealing with here.
Okay, I'm trying to like wrap my head around this Parton shower. It sounds pretty intense. So we're diving into this research paper, and it's literally called "Get This Quantum Walk Approach to Simulating Parton Showers."
Okay.
And yeah, it definitely seems like the science gets complicated quickly.
It does, yeah.
Yeah.
But the core idea is actually pretty straightforward.
Mm.
See, these Parton showers, they happen in places like the Large Hadron Collider.
Okay.
And what they do is they smash protons together at just mind-boggling speeds.
Wow.
These collisions are so powerful that they generate a whole shower of new particles, kind of like how if you strike a match, you create sparks that fly off in every direction.
So scientists are using these powerful colliders to essentially smash things together and see what pops out. Like, I can't believe that's an actual job, but why go through all that trouble? What's the point of it all?
Well, it's all about understanding the fundamental building blocks of our universe.
Okay.
You see, each particle interaction, when we see it in these showers, is governed by probabilities,
Probability.
kind of like a coin flip,
Okay.
deciding which way a particle will go.
Got it.
By studying these interactions, we can test our theories about how particles behave at the most basic level.
Okay, I'm starting to get the picture, but there's got to be more to it, right? What's the catch with these simulations?
Well, imagine if you had to predict the outcome of, let's say, 1,000,000 coin flips,
A million.
where each flip can lead to 1,000,000 more flips and so on and so on.
Oh, wow.
It's a mind-boggling number of possibilities to keep track of,
Yeah.
and even our most powerful computers really struggle to keep up.
So it's not just that the calculations are difficult, it's that there are so many that it would just take forever, right?
Exactly.
Yeah.
Simulating even a short Parton shower on a regular computer, a classical computer, can take a really long time. It's kind of like trying to map out every single route on a road trip,
Oh, wow.
including every wrong turn, every detour you could possibly take.
That sounds incredibly inefficient.
Yeah.
So how does this research offer a solution? Like, what's so special about using quantum computers for this kind of problem?
So that's where things get really interesting.
Okay.
You see, quantum computers, they play by a different set of rules. They use something called qubits. And unlike the regular bits in our everyday computers, they can explore multiple possibilities all at the same time.
At the same time.
At the same time, imagine a coin spinning in the air. It's both heads and tails at the same time, right?
Right.
Until it finally lands. That's the power of what they call quantum superposition.
Okay. I'm starting to see why this is a game changer, but how do we go from, like, a spinning coin to simulating a whole shower of particles? It still seems like a big jump.
It is a big jump, but that's where the concept of a quantum walk comes in, and it's at the heart of the research we're diving into today. Imagine a particle, and it's hopping around on a grid.
Okay, I'm picturing it.
Each step is like an interaction in the Parton shower.
Oh, okay.
And just like that spinning coin, it can explore multiple paths at once.
So it's like playing a board game where you roll the die to see how many spaces to move.
Right.
Only this time the die is quantum, and it's like all those parallel possibilities.
That's a great way to think about it. It's like the particle is taking every path on the board all at once, exploring all the different ways that the shower can unfold.
That is so cool. But what does this mean, like, practically speaking? Why is this quantum walk approach so much better than what we can do now?
Well, the researchers found that this approach, it requires far fewer qubits.
Okay, and fewer qubits is a good thing.
It is a good thing.
It sounds like they're, I don't know, a precious resource?
You could say that.
Yeah.
They're the building blocks of information in these computers. The fewer qubits you need, the less demanding the simulation is, the more likely we are to actually run it on the hardware that we have today.
So it's not just about doing the calculations faster. It's about being able to do them at all.
You got it.
This is incredible. It sounds like a whole new world of scientific computing is, like, opening up to us.
But there's even more.
What?
Not only does this new approach use fewer qubits, but it can also handle simulations with many more steps.
Okay.
This means we can study much longer periods of particle interaction. We get a more complete, more accurate picture of what's happening in these showers.
It's like finally getting like a high definition view of a process that's been like blurry and out of focus until now.
Exactly.
But I'm also curious, this research is all based on a model, right?
Right.
So how close are we to like actually simulating these particle showers as they happen in real life, like in the Large Hadron Collider, for example?
That's a great question. And the researchers do acknowledge that their model is still a simplification.
Okay.
This is really complex stuff.
Okay, so where do we go from here? What are the next steps in pushing the boundaries of these quantum simulations?
Well, that's where the real excitement kicks in.
Okay.
See, as these quantum computers, as they keep evolving, as they get more powerful, especially as we're able to, like pack more and more of those precious qubits into them,
Right.
we'll be able to add a lot more detail, a lot more complexity to these simulations.
Okay.
Eventually, we could get to the point where we're simulating Parton showers with like a level of realism that's just impossible, right? With even the most advanced regular computers.
That's mind-blowing. Like, we're on the verge of unlocking this whole new level of understanding about the universe. Like, what kind of mysteries could this unlock? Are we talking about things like dark matter? Or even understanding how the Big Bang unfolded?
You're thinking in exactly the right direction.
Okay.
Right now, our understanding of things like dark matter, it's limited by our ability to study these particle interactions, but at these incredibly high energies.
Okay.
With more powerful quantum simulations, we could, like, potentially recreate the conditions of the very early universe, something that we could never do before.
Oh yeah, now I'm really getting excited. But it also makes me wonder if these calculations are so mind-bogglingly complex that even our most powerful computers can't handle them, are we saying that one day quantum computers will just make them, like, easy?
Well, easy might not be the right word, but the key takeaway here is the potential.
Okay.
The potential for exponential speed up.
Exponential speed up.
Yeah. So there are some calculations that would take a classical computer, billions of years to complete. Those could potentially be done in a matter of hours, maybe even minutes, on a quantum computer that was powerful enough.
That's incredible. It makes my head spin just thinking about it. But it also sounds like we're still a ways away from that kind of quantum computing power, right? Like, it's not like I can order a quantum computer on Amazon just yet. So how long until these simulations become a reality?
You're right, we're not quite there yet. But the progress in this field has been absolutely staggering in recent years. It wasn't that long ago that quantum computers were purely theoretical. And now we're seeing the very first practical applications.
So it really feels like we're on the cusp of something truly revolutionary. It also makes me think this quantum walk idea, it's not just limited to particle physics, right?
No.
I bet there are tons of other fields where this could apply.
Absolutely. That's the beauty of fundamental research. The potential applications are so far-reaching.
Yeah.
This kind of quantum simulation could totally revolutionize fields, things like material science. We could design new materials with crazy properties that we never thought of before. Or what about drug discovery?
Oh, wow.
We could simulate how different molecules interact, but at the quantum level. Imagine the possibilities for new medications, life-saving stuff.
It's like opening a door to a whole new world of scientific exploration. We started off talking about smashing particles together at almost the speed of light.
Right.
And now we're talking about, like, curing diseases and designing materials from the future. It's amazing to see how it all connects.
It's incredible, really. And to think, this is still so new. We're just scratching the surface of what we can do with quantum computing. This research is really just the first step on a very long but exciting journey.
I love that. We're not just uncovering answers, we're uncovering new questions, new possibilities, things that we could never have imagined before. But speaking of questions, we haven't really dug into what this means for the future of quantum computing itself. It kind of sounds like we're still figuring out what these things are capable of.
Exactly. One of the most fascinating aspects of this research is that it shows us the potential of quantum computers.
Yeah.
But also the challenges in developing them.
So it's a bit of a chicken and egg situation. We need better quantum computers to run these simulations.
Right.
But the simulations will help us build more powerful computers.
Precisely. It's a very dynamic, very rapidly evolving field. This research, it's at the forefront, pushing those boundaries.
It's exhilarating to think about. It really does. It feels like we're witnessing the birth of this whole new era in scientific computing. It's like we're trying to build a rocket ship
Yeah.
to get to like a distant star,
Right.
But we're writing the blueprints as we go.
Exactly. Yeah.
But here's what really gets me.
Okay.
We've been talking about using quantum computers to understand the universe,
Right.
like at its most fundamental level.
Mm-hmm.
What if the universe itself is already some kind of quantum computer?
Now, that is a truly mind-bending thought.
Right.
And, it's not as far-fetched as it might sound. There are a lot of physicists that think the universe itself, that it might operate on these quantum mechanics principles
Okay.
that are just so much more profound than anything we understand right now.
So you're saying there might be this cosmic code
Yeah.
written in the language of quantum mechanics that governs everything.
It's a possibility.
Yeah.
And if we could crack that code, if we could think like the universe does,
Yeah.
who knows what we could accomplish,
It's exhilarating, but it's also a little bit terrifying.
right?
Like this idea that we're maybe standing on the edge of discoveries
I know.
that could just change our whole understanding of reality.
It's true. It's the kind of frontier that pushes the limits of what we can even imagine.
Totally.
And it just shows how important this kind of research is.
Yeah.
Curiosity-driven research.
Yeah.
Just the pursuit of knowledge for the sake of knowledge.
All right.
You never know where those explorations will take you.
That's what I love about these deep dives. We start with something that seems so specific, Yeah.
Like simulating these particle showers.
Right.
And we end up talking about, the nature of reality.
Exactly. It's a reminder that everything is connected, even in ways we don't always see at first.
Exactly. This whole conversation, it makes me think about this quote
Oh, yeah?
by the physicist John Wheeler.
Yeah.
He said, "We are not only observers of the universe, but we are participants. In some strange sense, this is a participatory universe."
I love that quote. That's perfect for this.
Right.
It really captures what we're talking about.
Yeah.
We're not just watching the universe happen. We're involved, We're trying to understand its secrets.
Mm-hmm.
And by doing that, we change how we see what's possible.
So what's the takeaway for our listeners today? What should they be thinking about after this deep dive into the world of quantum parton showers?
Well, I think the biggest takeaway is just how incredible this time in scientific discovery is.
Yeah.
And while it might seem like this research is, niche,
Mm-hmm.
it could really change our lives.
This quantum revolution is coming, and it's going to be amazing.
It's a fantastic time to be curious about the universe.
It really is.
And who knows, maybe some of our listeners will be the ones to make the next big discovery in this field. Until next time, keep those brainwaves buzzing.